Today we're going to go over the last section in Unit 5, which is about the fundamental theorem of algebra and the rational and irrational root theorem. I'm recording this so you can kind of start it and stop it as you need to copy some things down into your notes. And what I'm showing you right now, this is what's posted on the website, and it has these first 6 bullet points filled in. And so if you want to pause now to fill all this stuff in, we've talked about this in the last few lessons about when the remainder is 0, you have a factor, and the x-intercept is a root of the graph. This is all just kind of summarizing it, those concepts up. As you move down, okay, we have the fundamental theorem of algebra. That is the theorem we're going to talk about today, the first theorem we're going to talk about today. And what that's just saying is every polynomial equation with a degree greater than 0 has at least one root in the set of complex numbers. Or in other words, every polynomial is going to have a root. Okay, it could be real, it could be imaginary, but every polynomial is going to have a root. The corollary to that, okay, says every polynomial function of degree where the degree is greater than or equal to 1, has exactly n zeros, including multiplicities, and we'll explain that. We'll explain multiplicities when we run into that. But whatever your degree is, that's how many zeros you're going to have. Okay, so if you look at numbers 1, 2, and 3 here, okay, number 1, the degree is 3, you're going to have 3 zeros. Number 2, you have a degree of 4, you're going to have 4 zeros. Number 3, the degree is 2, you're going to have 2 zeros. So whatever the degree is, that's how many zeros or roots, okay, that you're going to have. Now, are they imaginary? Are they real? We don't know, okay, until we get into the problem. Okay, now jumping down to the bottom, 4, 5, and 6 are really problems that we've gone through in a previous unit, where given the zeros, write the polynomial. So in review, remember what you do is you set up parentheses for however many zeros you're given, in this case 3, and we're going minus in all 3 of them. Okay, hopefully this is starting to ring a bell for you. Variable comes first. Okay, the number then fits as the last term in each set of parentheses. So -2, +2, and 4. Now I'm going to clean this first parenthesis up. It's really x plus 2. The last 2 are the same. Okay, so there we've gone from our zeros, were -2, 2, and 4. Now, this line here, those are our factors. Now, to find the polynomial, I'm going to have to actually multiply those together. Okay, so these two, all right, a binomial times a binomial, I have to FOIL. Okay, and what I'm going to do is I'm going to ignore that for a few minutes. Okay, so if I FOIL those two together, first times first is x squared, outside times outside, -2x, inside times inside is +2x, last times last is -4. Okay, so did all that, and I still eventually going to have to multiply that times x minus 4. Now I'm going to simplify this polynomial because -2 plus 2x is 0, which leaves me with just x squared minus 4. Doesn't always happen that way. We get kind of lucky here. And then we have to multiply that times that third factor. And again, I have a binomial times a binomial. So first times first is x cubed. Outside times outside, 4x squared. Inside times inside, -4x. Last times last is +16. Okay, now this right here, you would always check to see if there's like terms you can combine, but I can't. Okay, I can't. There's no like terms there, so that's my answer. Okay, that's my polynomial in simplest form. Now, if you want to know what the answers are for 5 and 6, you could jump back to the website and take a look, or you can check this out here. There you guys have the answers to 5 and 6. Okay, notice in 5 that one of our zeros is a 0. Okay, so that x represents the factor of 0, because it would start as x minus 0, which is just x. Okay, the answer to 5, 3x cubed minus 11x squared plus 4x. the answer to 6, 2x cubed minus x squared minus 8x plus 4. Okay, now, you can pause the video and write all that work down if you want, or try those on your own and see if you can get the answers that are shown here. Okay, so the majority of the notes today we're going to be talking about the rational root theorem. Okay, the rational root theorem gives us a way, if we don't know any of the roots, all right, it gives us a way to kind of guess what those roots might be. Okay, so the rational root theorem says this: the possible rational roots. So we're not talking here about imaginary roots. These are just the possible rational roots, or the zeros, okay, or the x-intercepts, not your imaginary. Okay, the possible rational roots, okay, they are equal to, all right, I'm going to give you a ratio here. The numerator is the factors of the constant and the denominator are the factors of the leading coefficient. Now, those are long phrases, factors of the constant and factors of the leading coefficient. We reduce that to P's and Q's, okay? We call the factors of the constant P and the factors of the leading coefficient Q, okay? So we're going to do an example here. We're going to generate a lot of possibilities, okay? So in this example right below, we have 2x cubed minus 11x squared plus 12x plus 9. Okay, my leading coefficient, okay, my leading coefficient, okay, I'm going to highlight here in yellow. Okay, my leading coefficient is 2. Okay, so that's Q. Or in other words, the factors of 2 are Q. Okay, remember factors are the numbers that multiply to get us that value. So to get 2, all right, to get 2, I could use 1 or 2. Okay, now the P are the factors of my constant. 9's my constant, so the factors of 9 are going to be my numerator or my P values. Okay, well, what are my factors of 9? 1, 9, and 3. Okay, now we find the ratio of every combination. Okay, so if I start with this 1, I'm going to take that 1 and divide it by everything in the denominator. So 1 divided by 1 is 1. 1 divided by 2 is 1/2. Okay, then I have to do the same thing with 9. I'm going to take 9 and divide it by everything in my denominator. 9 divided by 1 is 9. 9 divided by 2, we're going to write it as 9/2. And then lastly, do everything with that third factor in the numerator. 3 divided by 1 is 3. 3 divided by 2 is 3/2. Now, that's every combination, and if you approach it that way, numerator divided by denominator, and go through every possibility, you'll eventually get through all the different possible rational zeros. Now, one last thing. All of these could be either positive or negative. Okay, so it's really plus or minus, 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 plus or minus. Okay, you have to account for both the positive and the negative factor. Okay, so this is a brand new concept. It's going to take a few to get this down. Okay, so let's do a couple more. Okay, so in number 7. Okay, in number 7, my leading coefficient is this number in front of x cubed, which is 1. Okay, so 1 is my leading coefficient. All right, those are my P's. What are my factors of P? Well, 1. Okay. Well, let me go back. Sorry, that's Q. My apologies. Okay, leading coefficient is Q. Let me erase that. Q. Okay, so my factors of Q are 1. All right, I'm going to move this down here because Q is in the denominator. That's my fault. Okay, factors of Q are 1. Now, the factors of P. Okay, P, all right, is your constant. Okay, our constant is negative 24. Okay, so negative 24, or the factors of negative 24, are going to be my p-values. So what are the factors of 24? 1, 24, 2, 12, 3, and 8, 4, and 6. Okay, those are all factors of negative 24. Now, my final answer, okay, is I'm going to take the ratio of P to Q. Okay, so P divided by Q equals, and what I'm going to do is I'm going to put a plus minus here, and I'm going to pretend that applies, not pretend, but I am going to make sure we all understand that applies to every ratio we have here. Okay, so start with 1. Okay, 1 over 1 is 1. P over Q. 24 over 1 is 24. 2 over 1 is 2. 12 over 1 is 12. 3 over 1 is 3. 8 over 1 is 8. 4 over 1 is 4. 6 over 1 is 6. Okay? So these are all the possible rational roots of number 7. Okay? Those are all the possible rational roots of number 7. Okay, let's do another one. Let's take a look at number 8. 16 is my constant. That's my p-value. Okay? All right? And let me write it this way just so we don't think it's 16 times p. 16 is my p-value. My factors of 16 are 1, and I'm going to write them in numerical order this time. 1 and 16, 2 and 8, and 4. Those are all my factors of 16. Okay, now Q. Okay, Q is equal to 2. That's my leading coefficient. So those factors are just 1 and 2. Okay, so my possible rational roots are P divided by Q, plus or minus positive and negative root. Okay, I'm going to start with this one and divide it by all of these factors here and here. So 1 divided by 1 is 1. 1 divided by 2 is 1/2. Okay. Then I'm going to do the same thing with the 2. Okay. Do the same thing with the 2. And I'm going to have to divide that by everything you see in blue there. So 2 divided by 1 is 2. And then 2 divided by 2 is 1. But I already have 1 listed, so I don't need to list it again. Do the same thing with the 4. 4 divided by 1 is 4. And then 4 divided by 2, let me move this here. 4 divided by 2 is 2, which I already have listed, so I'm not going to list it again. Now I'm going to take this 8 and divide it by both of those blue numbers. 8 divided by 1 is 8. 8 divided by 2 is 4. Okay, now, I already have a 4, so I don't need to write it. But I do need that 8. Okay, and then finally, we're going to take 16. Okay, we're going to take 16 and do the same thing. 16 divided by 1 is 16. 16 divided by 2 is 8. Okay, but again, I already have 8 there. I don't have to rewrite it if I don't want to. So these numbers right here are all the possible rational roots of that polynomial you see in number 8. Okay, and then finally number 9 you see here. Okay, my P's are my factors of 12. You see them listed there. My Q's are my factors of 3. You see those listed there. And then P over Q, that's the ratio of every combination you could have there. And notice I didn't repeat anything. Okay, leave things as fractions. Okay? If you need to pause the video to write all that down, do it. Then start it back up and we'll move to the irrational root theorem. Okay? Remember, irrational roots, those are your imaginary roots. Those are your those are the ones with the I. Those always come in conjugate pairs. Okay? So for example, if you know one of your roots is 1 plus well, let me go back. It includes I, but it also includes roots that have square roots that are not perfect squares. That's also an irrational root. Okay, so the example we have here is, all right, without I, all right, but this same concept, okay, would include, all right, when you have I in there, but they come in conjugate pairs. So if you know one of your roots is 1 plus the square root of 2, then 1 minus the square root of 2 is also a root. We've talked about conjugates over the course of the year. You should understand what that means. So if you have an irrational root, which means one of two things, it either has an I or there's a square root of not a perfect square, then they always come in conjugate pairs. Okay? Okay, so here's what all of this stuff we've been doing in this unit has been building up to. When you are given a polynomial like you see in number 10, okay, and I want to know what the roots are, okay, well, how do I find it? Okay, all right, well, I could try and factor it, and I could try and take, in this case, since there's 4 terms, I could try to group it, but what if factoring doesn't work? Okay, I need another method, okay, and that's what all the stuff we've learned, okay, in this chapter is leading us up to, okay, so the first thing you do, okay, and the steps are listed here, the first thing you do, because this is a little different, we're not given one of the roots. We don't know, okay? The first thing you do is use the rational root theorem, your P's and your Q's, to list all the possible rational zeros, okay? So if I went through here and I worked my P's and my Q's, okay, so P would be the 12 is the constant, so it would be the factors of 12 would be P. That would be 1, 2, 3, 4, 6, and 12. All right, and then Q. Let's see. Q is my leading coefficient, which is 1. So 1 equals Q, and my factors of that are just 1. Okay, so all my possible rational zeros, which are my P's over Q's, would be plus or minus 1, 2, 3, 4, 6, and 12. Okay? All right? That's the first step. Okay? Now, number 2. Number 2 is guess and check. What you're going to do is you are going to choose one of these numbers here, use synthetic division, and see if it's a root. Now remember, when your remainder is 0, that's what tells us, okay, that's what tells us that something is a root, okay? All right, so we are going to pick one of these numbers, use synthetic substitution, and see if our remainder is 0. Okay, now, in this example, it's already set up for us. They want us to choose, they want us to try 1 first, okay? So 1 is in our list here that I've circled, and I'm going to use synthetic substitution in our polynomial. So I've got 1x cubed, negative 3x squared, negative 4x, and 12. Bring the 1 down. 1 times 1 is 1. Add, I get negative 2. Multiply, add, I get negative 6. Multiply, add, I get 6. Now, what this number tells us right here is that 1 is not a root, okay? That number has to be 0 in order for it to be a root, okay? So 1 is not a root. So if this happens, then you've got to pick another number and use synthetic substitution again. Here they want us to choose 2. Okay? So 1, negative 3, negative 4, and 12. Bring the 1 down. There it is, 0. Okay? So this 0 right here What that tells us is that 2 is a root. Okay? That's what that tells us. 2 is a root. Now, we're going to go back to what we talked about last week, okay, when we used synthetic substitution and we found one of the roots. Then remember what we used, and you did this a couple times last week. What we use is we use this part, we write the polynomial, and we factor it. Okay? So those numbers would give me this polynomial. Okay? 1x squared minus x minus 6. Okay, and again, that's from those numbers right here. I start with an x squared because my original polynomial had a degree of 3. So I start this depressed polynomial with 1 degree less. Okay, and now I'm going to factor that. So I need two numbers that add up to -1, multiply to be -6. That's going to be -3 and 2. So x minus 3 times x plus 2. Okay, now from there I need to get my roots. Okay, so I use the zero product property. Set each factor equal to 0. Okay, and this would be 3. And this would be -2. Okay, now there's room in that little box there to write all our roots. Okay, and in numerical order, our roots are -2, 2, and 3. Okay, turn to number 13. Okay, all right, so in number 13, if I went through my P's and my Q's, okay, because that's the first step, P over Q is going to generate for me this list. Plus or minus, and they're all plus or minus 1, 2, 3, 4, 6, and 12. Okay. All right, so then I am going to use synthetic substitution with one of those numbers. Okay. I'm going to go ahead and I'm going to choose -3. Now, for time's sake, I'm kind of ahead of the game. I know what I should choose, but you don't. So for you, it's going to be a guess and check. Okay, so I'm going to choose -3, and that here are my coefficients. Then we do our synthetic division. Bring the 1 down, and then multiply and add the rest of the way. Okay, I get 0. Okay, so that tells me, all right, that -3 is one of the roots, okay, or the zeros. Okay, so I'm going to start to make my list. Okay, my roots. One of them is -3. Okay, then I'm going to write my polynomial that's generated from these numbers right here. Okay, that polynomial is going to be 1x cubed minus x squared minus 4x plus 4. Okay, now the rule is to factor this. I've got 4 terms, so I use grouping. Okay, group, group. GCF is x squared, leaves me with x minus 1. GCF is -4, leaves me with x minus 1. And then my final answer, in terms of this factoring here, remember, would be x squared minus 4 times x minus 1. But are we done? I have a difference of perfect squares with the x squared minus 4. So I have to continue to factor that. That'd be x minus 2 times x plus 2 times x minus 1. Okay, let's use my zero product property. X minus 2 equals 0. X plus 2 equals 0. X minus 1 equals 0. All right, and this would give me x equals 2. So that means I have a root of 2. This next one gives me -2. So I have another root of -2. And then I have a root of 1. So 1 would be the last one. And those are my roots for number 13. Now, Notice my degree is 4. That means I'm going to have 4 roots. Okay, now let's take a look at number 14. If I were to generate my P's and Q's, here's what I would have. Plus or minus 1, 2, 3, 4, 6, and 12. Okay, so again, here we would choose, it's just a guess. I'm going to choose -3 again. And use synthetic substitution, 1x cubed, 1x squared, -10x, -12. Do my work here. Get 0. Okay, so when I start to write my solutions, okay, my zeros, I now know that -3 is one of my zeros. All right, now we'll write our polynomial we get here. That's going to be 1x squared minus 2x minus 4. And I ask myself, in this case, because I need to factor it, what adds up to -2 and multiplies to be -4? Nothing. There's nothing that would do that. So this happens to be prime. It doesn't factor. So how do we get the zeros from it? How do we get our next 2 solutions? Because my degree is 3, there's 2 more solutions I need to find. Well, if you can't factor a second degree polynomial, which is what this is, we use the quadratic formula. Okay. A is 1, B is -2, C is -4. Okay, so x is equal to the opposite of b, plus or minus the square root of b squared, so 2 squared is 4, minus 4 times a times c, all over 2 times a. Okay, when we simplify all that, it's going to be 2 plus or minus 2 times the square root of 5, all over 2. And then that's going to be 1 plus or minus the square root of 5. There's my other 2 zeros. 1 plus the square root of 5 and 1 minus the square root of 5. I have a degree of 3. I'm going to have 3 zeros in there. They are. Okay, last thing I'm going to touch on is this complex conjugate theorem, and I mentioned it earlier with the rational conjugate theorem, is that when you have complex conjugates, they come in pairs. So if a plus bi is a root, then a minus bi is a root. Okay, they come in conjugate pairs. Okay, so for example, in number 16, the directions here say find the missing zeros, so that's all we're going to do. All right, I'm given that these 2 are zeros. Well, this is a complex number, so that means not only is this a root, but its conjugate also is a root. Okay, so 1 minus I would be the missing roots, and this or these are all the roots. Okay, going back to 15, if positive 4i is a root, then negative 4i is a root. It's conjugate. And here's a list of all the roots. Okay. All right, and then in 17, all right, this is an irrational root, so that means its conjugate is also a root. So the missing root would be the square root of 5. Here's a list of all the roots. Okay, now if you jump to the website again, which that's going to look like this, there's a lot more problems done for you. You can practice if you want, and obviously if you have any questions, let me know.